Students, this is M. Prasant Raju, stand before you to continue the classes of engineering mechanics. Today, we would like to start the unit number 4 named as Kinematics and Kinetics. Let us see this. Before I am going to start the unit 4, Kinematics and Kinetics, let us know the definitions of Kinematics and Kinetics respectively. The first definition is, what is kinematics? Study of bodies which are in motion without considering the forces. Without considering the forces is called kinematics. The second one is kinetics. It deals the study of bodies which are in motion with considering the forces is called kinetics. Now, after knowing the definitions of kinematics and kinetics, as I told you in the beginning that, let us repeat once again, kinematics means it deals the study of bodies which are in motion without considering the forces called kinematics. And whereas kinetics represents, it deals the study of bodies which are in motion with considering the forces is called kinetics. Now, we are going to enter into the types of motions. Let us see this. Types of motion. The first motion is rectilinear motion. Rectilinear motion. The second one is rotatory motion. The third one is plane motion. Let us explain the types of motions one by one. First one is rectilinear motion, second one is rotatory motion, the third one is plane motion. The first one is rectilinear motion. It represents that a path traced by the body which is in straight line, then it is called rectilinear motion. I will explain this rectilinear motion by drawing a diagram like this. Let us consider that there is an initial point like this, denoted by say some A, and final point is denoted by say some B. If I would like to join the line from A to B like this, and the arrow mark represents that the direction of this particular body is moving from point A to the point B, then we are going to call it as rectilinear motion. That means, strictly speaking, that a path traced by the body which is in straight line, then it is called rectilinear motion. For example, What are the best examples coming under this rectilinear motion? The first example is, example 1 is moving a train in a straight track and the example 2 is a man walking on flat road in straight path. These are the best examples coming under rectilinear motion. As I told you very clearly that a path traced by the body which is in straight line, then it is called rectilinear motion. The example 1 is moving a train in straight track and a man walking on flat road in straight path, which is known as the examples of coming under rectilinear motion. The second one is rotatory motion. Let us see this. The second one is rotatory motion. How do we define this? A path traced by the body, which is in circle, then it is called rotatory motion. I would like to draw the diagram towards explaining rotatory motion like this. If you take a circular path like this, in the direction of a body starting at a point A on the circle and it moves in clockwise direction and it moves clockwise direction by passing through the point B, we could consider it as rotatory motion. I would like to give example 1. Example 1 is motion of blades of ceiling fan and example 2 is rotation of earth with respect to circular axis. These are the best examples coming under rotatory motion. As I told you very clearly that the rotatory motion is defined as a path traced by the body which is in circle, then it is called rotatory motion, which is in circle. Then if you are going to see this diagram, the body started at a point A and it moves towards the point B in clockwise direction and it continues like this. If the body is ready to move from the point A to B, again B to A. Suppose if you consider this diagram, a body is traveling from point A to point B in clockwise direction and again B to A is in anti-clockwise direction. So strictly speaking that the body is completely rotating in clockwise direction from the point A to point B towards the point B. Therefore, I would like to take the examples towards this rotatory motion is, example 1 is motion of bodies of ceiling fan and motion of blades of ceiling fan. Example 2 is rotation of earth with respect to the circular axis. Now we are going to enter into the third one is plane motion. The third motion is plane motion. Plane motion is defined as it is the combination of rectilinear and rotatory motions, of a body is called plane motion. If I would like to draw a diagram towards explaining both rectilinear and rotatory, it should be constructed like this. I would like to take first of all a body which is existing in A, this is a point A, this is a point C, and it goes like this. If you take this diagram, I would like to take like this. This is a point from here to here, like this. This is called point B, and this is called point C. So, strictly speaking, that a motion consisting both rectilinear and rotatory is called what? Plane motion. Now, after knowing the types of motion, now we are going to enter into the equations of motion under gravity. Let us see this. Before I am going to explain the equations of motion under gravity, there are three most prominent definitions towards explaining the kinematics of a body. Let us see this. The first basic definition towards explaining kinematics is, number one is distance. Usually, this distance is denoted by a letter S. The change of position of a body, the change of position of a body without reference to direction is called distance. It is denoted by S. The SI unit of distance is meter. The second definition is displacement. Displacement, it is denoted by S bar. Strictly speaking, that distance S is scalar quantity, displacement S bar is vector quantity. Let us see the difference between vector and scalar. When do we say that a physical quantity is said to be a vector? A physical quantity will have both magnitude and direction, we are calling it as a vector, and a physical quantity possessing only magnitude but not direction, we are calling it as a scalar. So, how do we define this displacement? The change of position of a body with reference to direction is called displacement. It is denoted by S bar. The SI unit is meter. I would like to explain the difference between distance and displacement. Okay, distance is denoted by S. It is a scalar quantity. The change of position of a body without reference to direction is called distance. Okay, that means it is possessing only magnitude. It does not have direction. Whereas displacement is a vector quantity. The change of position of a body with reference to direction is called displacement. It is denoted by S bar because it is a vector. It will possess both magnitude and direction. But the SI unit of both the parameters is same. What is that? You know, if you take distance, it is measured in meters, and as well as displacement, S bar is also measured in meters. And the consequent next definition by explaining kinematics of a body is velocity. Let us see this. The third definition is velocity. It is denoted by V bar, the rate of change of displacement is called velocity. It is denoted by V bar. Now, I would like to explain this velocity V in mathematical representations. If you want to like, V bar is equal to d by dt of S bar. So, this was the mathematical form towards explaining a parameter like velocity. So, what is velocity here? The rate of change of displacement is called velocity. Another definition is the first derivative of displacement is also gives what? Velocity. So, that means strictly speaking here, if you are going to differentiate a vector quantity like a displacement, again you will get a vector which is denoted by what? V bar. So, how do we write this? V bar is equal to d by dt of S bar. What is the SI unit of this velocity? Let us see this. The SI unit of velocity is meters per second. Meter per second. This was the exclusive SI unit. Now, based on this velocity, we are going to define one more definition which is called acceleration. Let us see this. The fourth definition is acceleration. It is denoted by A bar. It is defined as the rate of change of velocity is called acceleration. It is denoted by A bar, which is also a vector quantity. In mathematical representations, how could we represent this acceleration A bar? Let us see this. A bar is equal to V minus U by T. So, this was the fundamental mathematical form towards explaining acceleration. That means A bar is equal to V minus U by T, where V is called final velocity, U is called initial velocity, and T is called time. Okay. So, we are measuring the rate of change of velocity, that means acceleration. It is nothing but in the denominator it will be change of velocity, and in the denominator it will be time. It will be in the numerator it will be change of velocity, and in the denominator it will be taking time. So, therefore, if I am going to divide the change in velocity with the time, I would be able to get what? Acceleration. So, how do we write this? A bar is equal to V minus U by T, where V is final velocity, U is initial velocity, and T is called what? Time. One more definition I can represent that acceleration is A bar is equal to d square S bar by dt square, or another mathematical form I would like to explain for this acceleration is A bar is equal to dV bar by dV bar by dt. So, this is another mathematical form. So, if you look at these three differential forms, my dear students, my A bar is equal to V minus U by T. That means final velocity minus initial velocity by time, you could get acceleration. My acceleration is equal to second derivative of displacement, you could get acceleration. And in another way, my acceleration A bar is equal to rate of change of velocity, or we can define like this, the first derivative of velocity is also gives what? Acceleration. So, therefore, there are three mathematical forms towards explaining a definition like acceleration. Number one is the rate of change of velocity is called acceleration. Second one is A bar is equal to second derivative of displacement is also gives acceleration. And the third one is A bar is equal to first derivative of velocity or rate of change of velocity is given by acceleration. Therefore, A bar is equal to again dV bar by dt. After knowing these three mathematical fundamental definitions like displacement, velocity, and acceleration, based on these three parameters, we are going to explain equations of motion under gravity. Let us see this. Equations of motion under gravity. The equations of motion under gravity is majorly classified into the four types. The first one is known as V is equal to U plus AT. The second one is S is equal to UT plus 1 by 2 AT square. The third one is V square minus U square is equal to 2AS. The fourth one is Sn is equal to U plus A into n minus 1 by 2. These are the four major equations represented by equations of motion under gravity. Now, I would like to take the two special cases. When do we change these four equations according to the first case and second case? That is, the special cases are actually be classified into the two categories. The first category is equations of motion under gravity in freely falling condition and equations of motion under gravity when they were in projected vertically upward direction. Let us see this. Case 1. Equations of motion under gravity under gravity when they are in freely falling condition. Freely falling condition. Let us see this. The first equation of equations of motion under gravity will change like this. So, what are the changes that we require to construct the equations of motion under gravity when they were in freely falling condition? Whenever a body is ready to fall from a certain height, its initial velocity is becoming 0 and its acceleration due to gravity is becoming positive direction. That means I can say like this. So, the first one is initial velocity u is equal to 0 and my acceleration a is equal to plus g. These two are taking place when equations of motion under gravity when they were in freely falling condition. Let us see this. So, if you bring both of them and substitute in the four equations, I will get like this. The first one is V is equal to U plus AT. We know that this is the standard form, first form. So, if I bring U is equal to 0 to substitute here and A is equal to plus G, bring it and substitute in this equation, I will get like this. V is equal to 0 plus GT. That means V is equal to how much? GT. So, the first equation of V is equal to U plus AT, change it like this by getting changes U is equal to 0 and A is equal to plus G, especially in first case. What is that first condition? Freely falling condition. So, therefore, whenever a body is ready to fall under a certain height, its initial velocity U is equal to 0 and its acceleration due to gravity is equal to plus G. Therefore, then this equation will change like this. So, V is equal to U plus AT, we know that it is a standard form of equation of motion under gravity. After bringing U is equal to 0 and A is equal to plus G to this equation, my equation will change like this. V is equal to 0 plus GT, V is equal to GT. Similarly, we will see the three remaining equations of motion under gravity. Let us see. The second one is S is equal to UT plus 1 by 2 AT square. So, bring U is equal to 0 and A is equal to plus G, I will get S is equal to 0 into T plus 1 by 2 GT square. After substituting and simplifying, S is equal to 0 into T, 0. Therefore, we will get the remaining term is S is equal to 1 by 2 GT square. This is what is known as the second equation. Similarly, we will see the third one. The third one is V square minus U square is equal to 2AS. This is a standard form of equations of motion under gravity. Now, I am bringing U is equal to 0 and A is equal to plus G, substitute in the respective positions of that equation. I will get V square minus 0 is equal to 2GS. After simplifying this, we will get V square is equal to 2gs. This is what is known as the third equations of motion under gravity when they are freely falling condition. Let us see the fourth one, how it will be changes. The fourth one is Sn is equal to u plus a into n minus half. This is a standard form. And after bringing u is equal to 0 and a is equal to plus g and substitute in their respective positions, I will get Sn is equal to 0 plus g into n minus 1 by 2. And after simplifying this, I will get Sn is equal to g into n minus 1 by 2. This is the fourth equations of motion under gravity when they were in freely falling condition. So therefore, the first one is v is equal to gt, the second one is 1 by 2 gt square, the third one is v square is equal to 2gs, and the fourth one is Sn is equal to g into n minus 1 by 2. These are the changed equations when they were existing in freely falling condition. Similarly, the second case is equations of motion under gravity when they were vertically projected upward direction. Let us see this. The second case is case 2, equations of motion under gravity when they are vertically projected in upward direction. Equations of motion under gravity when they are vertically projected in upward direction. So what type of changes happens whenever a body is ready to project from downward direction to upward direction? Let us see this. Usually when we throw a body from downward direction to the upward direction, what happens, there is no change in its initial velocity. So it remains the same. That means my initial velocity is as it is, whereas my acceleration due to gravity is becoming negative, because when I am throwing a body from downward direction to upward direction, my acceleration due to gravity is taking negative. That means we can represent like this. My initial velocity u is as usual, there is no change at all, and my acceleration due to gravity a is equal to minus g. These two are the changes happened when equations of motion under gravity when they are vertically projected in upward direction. Now, bring these two values and substitute in their respective four equations. Those four equations will be changed like this. The first one is known as v is equal to u plus at. So bring u is equal to u as usual. That means initial velocity remains the same. Acceleration due to gravity changes by negative direction. Therefore, I can get v is equal to u minus gt. The first equation change like this. The second equation, s is equal to ut plus half at square. So it changes like this. S is equal to ut minus 1 by 2 gt square. And the third equation changes like this. V square minus u square is equal to 2as. This is the standard form, and it changes like this. V square minus u square is equal to minus 2gs. And the fourth equation is Sn is equal to u plus a into n minus half. This is the standard form, and after changing this, Sn is equal to u minus g into n minus 1 by 2. So if you look at these four equations, my dear students, you could understood how the general equations under motion of a body are changes like this. The first one is v is equal to u plus at. Okay, bring u as there is no change. Bring a, there is a change, negative direction of acceleration due to gravity. So my equation will change like this. V is equal to u minus gt. Similarly, the second equation, s is equal to ut plus half at square. This is general form. And bring u is equal to u and a is equal to minus g. I will get s is equal to ut minus 1 by 2 gt square. Similarly, the third one is v square minus v square is equal to 2as. Bring u is equal to u as there is no change in it, and a is equal to minus g, that is in negative direction. I could get v square minus v square is equal to minus 2gs. And similarly, fourth one is Sn is equal to u plus a into n minus half. Bring u is equal to u as usual, there is no change at all, and g a is equal to negative direction of motion of a body. Therefore, Sn is equal to u minus g into n minus 1 by 2. So, after knowing these two special cases of equations of motion under gravity, now we would like to derive how to get the expression of V is equal to U plus AT, how to get the equation of S is equal to UT plus half AT square, how to get V square minus V square is equal to 2S. Let us see this. The derivative parts of V is equal to U plus AT, S is equal to UT plus half AT square, and V square minus V square is equal to 2S. Let us see this. Derivations of equations of motion under gravity. The first one is V is equal to U plus AT. Derive V is equal to U plus AT. Let us see this. Consider proof. Consider the initial velocity is equal to, say, some u, final velocity of the body v, change in velocity of the body is equal to final velocity minus initial velocity that is equal to v minus u rate of change of velocity is equal to v minus u by t. But by definition of acceleration, we know that rate of change of velocity is equal to what? Acceleration of the body. Therefore, in place of rate of change of velocity, I could substitute A. A is equal to v minus u by t. Taking cross multiplication, we will get AT is equal to v minus u. Now, after rearranging, we will get like this. Rearranging, we will get AT is equal to v minus u. If you bring v to left hand side, I will get like this. V minus u is equal to AT, and if you bring minus u to towards right direction, we will get v is equal to u plus. This was the standard form. So, the way to derive the expression for v is equal to u plus AT is like this. I would like to repeat it once again. Derive v is equal to u plus AT. Whenever, if we ask the question like this in the examination, how to prove this? Derive v is equal to u plus AT. Proof. Consider the initial velocity of the body is equal to u, final velocity of the body is equal to v, change in velocity is equal to final velocity minus initial velocity, that can be written as v minus u, rate of change of velocity is equal to v minus u by t, and taking cross multiplication, that AT is equal to v minus u, and after rearranging we will get v minus u is equal to AT, therefore v is equal to u plus AT. This is the way of methodology to get the expression for v is equal to u plus AT. Similarly, we will go for the second derivation. Derive S is equal to ut plus 1 by 2 AT square. Proof. Consider the initial velocity of the body, is equal to u, final velocity of the body is equal to v, change in velocity is equal to final velocity minus initial velocity, rate of change of velocity is equal to v minus u by t, average velocity of the body this can be written as v plus u by 2. Now we have a standard formula for distance traveled by the body is equal to average velocity into time. Let us see this. Distance traveled by the body is equal to average velocity into time. So how could we write this in mathematical formulations? S is equal to v plus u by 2 into t. So let me explain what are the terms that are existing in this formula. S is equal to v plus u by 2 into t. My S is distance traveled by the body and my v is average velocity, that is final velocity, and my u is initial velocity. So when do we able to get average velocity? What are the participating velocities we have? Add both of them and divide with 2. So we will get what? S is equal to v plus u by 2 into t. I have only two velocities here. What are they? Initial velocity and final velocity. So let both are combined and to divide with 2, I would like to call it as average velocity. Therefore, S is equal to v plus u by 2 into t. In place of v, we know that u plus at from equation 1. So I could change like this. S is equal to u plus at plus u plus at plus u by 2 into t. After simplifying this, u plus u is equal to how much? 2u. Therefore, S is equal to 2u plus at by 2 into t. Okay. Now, after simplifying this part, we will get here. After simplifying this, S is equal to 2u into t, 2ut. S is equal to 2ut plus at into t, at square divided by. So, if you look at this equation, after getting this, this was in the form of what? A plus b by 2. How could we write this? A by 2 plus b by 2. So, if you split like that, S is equal to 2ut by 2 plus at square by 2. So, here 2 to cancel here and the remaining term is S is equal to ut plus at square by 2, and after simplifying this, I will get the final expression S is equal to ut plus 1 by 2 at square. This is what is known as the ultimate second equation of derivation of equations of motion under gravity. What is that? S is equal to ut plus 1 by 2 at square. So in this equation, my S represents distance traveled by the body, my u is initial velocity, t is equal to time, and a is equal to acceleration. Similarly, in the similar pattern, we are going to derive the third equation of motion under gravity, which is known as v square minus u square is equal to 2s. Let us see this. The third one is derive v square minus u square is equal to 2as. Let us see this proof of the third expression, which is known as consider the initial velocity of the body is equal to u, final velocity of the body is equal to v, change in velocity of the body is equal to v minus u by t, average velocity of the body is equal to v plus u by 2. Now we have a standard form. What is that? Distance traveled by the body is equal to v plus u by 2 plus 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 v plus u by the body, distance traveled by the body is equal to the average velocity into time. If I would like to convert this formula into mathematical representations, I will get like this. S is equal to V plus U by 2 into T. So, strictly speaking, my dear students, S is called distance traveled by the body, V is called final velocity, U is initial velocity, and the combination of both of them divided with 2 to consider it as average velocity. What is T? Time. Now, this T can be written as, for our convenience, by definition of acceleration. I will get the expression for T like this. S is equal to V plus U by 2 into V minus U by A. So, where this expression came? I am going to write here, reasoning here. Since A is equal to V minus U by T. This was the definition of, a standard definition of acceleration. If you see A is equal to V minus U by T, so how do we define this? Acceleration is equal to rate of change of velocity by time. So I would write this A is equal to V minus U by T. If we bring A to here and T to here, I will get what? In place of T, I can write V minus U by A. Now, strictly speaking, while looking through this equation, we will get one idea. This is V plus U, that is A plus B. This is V minus U, this is A minus B. We have a standard formula. A plus B into A minus B, nothing but A square minus B square. In the similar pattern, I can get S is equal to V square minus U square by 2A. Now, after taking cross multiplication, I will get my left hand time is 2AS is equal to V square minus U square. Now, rearranging. After rearranging this equation, I will get like this. 2AS is equal to V square minus U square. Just bring right hand side term to left hand side term to right hand side. I will get like this, followed by V square minus U square is equal to 2AS. This was the required expression. V square minus U square is equal to 2AS. Therefore, V square minus U square is equal to 2AS. In this expression, my dear student, equation, V is called final velocity, U is initial velocity, A is acceleration, and S is called distance traveled by the body. This is the way of pattern of getting the expressions for derivations of equations of motion under gravity. As I told you in the beginning that the equations of motion under gravity is classified into the 4 types. One is called V is equal to U plus AT. Second one is S is equal to UT plus half AT square. Third one is V square minus V square is equal to S. And fourth one is Sn is equal to U plus A into N minus. So, the remaining part of this kinematics will continue in the next class. Thank you very much.